All right, so we're going to look at what are called vector projections now. So some of the prior knowledge for this would be the previous three lectures on vectors, where we looked at an introduction, we looked at resolving vectors into rectangular components, and then we also looked at the dot product. And something that will also be useful for this video is just this idea of unit vectors, because that's going to be coming up a bit. The key concepts we'll cover in this will just be what's called the vector resolute and the scalar resolute. Um, And yeah, it's probably the most challenging idea we've covered in vectors so far. So let's get into it. So before we sort of do the maths behind it, let's just think about what a vector projection is. So a vector projection is basically a way that we can quantify how much one vector points in the direction of another vector. So if we just look at this diagram here for a moment, if we've got vector A sort of pointing here to here, and then you've got vector B, which is this long vector underneath, we can see that vector u, is the amount that vector A is pointing in the direction of vector B. And a good analogy I heard once was a flashlight. So if you're at the top of A and you were to shine a flashlight onto B, the length from this starting point to where that light hits is going to be your vector projection of A onto B. Okay, and so what we'll do is we'll put some formality around it. So the vector resolute of A in the direction of B can be expressed in any one of the following forms. We'll come back to these in a moment. We're just going to explain where this first part comes from. So let's just read it first. So we say that vector U is vector A dotted with vector B divided by the dot product between B and B and then multiplied by vector B. And then these are just alternate forms, which we'll come to in a moment. But let's just see if we can explain this first part. So from the diagram, we can see that A equals U plus W. And I think that should make sense. Vector A here is vector U plus vector W. I wasn't able to put an arrowhead on W, but W is pointing in that direction because the direction's important, right? So A is U plus W. Okay, and U is KB. Now, K is a scalar multiple. K is just a real number. And so you can see that U is just a multiple of B, because B is pointing in the same direction as U. So U is a scalar multiple of B. And so what we can say is W equals A minus U. Okay, let's think about W being A minus U. Okay, W, remember, is pointing in this direction, is the same as A minus U. All right, A is here. Now we're doing vector subtraction minus U. So that's negative U would point this way. And so we would get by doing that vector subtraction, you would get the vector W, which would be the same length going there. So A minus U would give you W. And we know that U is just a multiple of B, right? So we can say we can replace vector U with KB. So we get that W equals A minus KB. Okay. The other thing we can say is that for W to be perpendicular to B, we must have that the dot product between W and B is 0. Okay, so this vector W is perpendicular to B. So remember, when we take the dot product, if they're at right angles to one another, it goes to 0. And that should make sense if you just recall what the dot product is. Cosine of 90 degrees is 0. So again, for W to be perpendicular to B, we must have that the dot product between W and B equals 0. But we just showed that W is A minus KB. Okay, so A minus KB multiplied by vector B must equal 0. Okay, just using some properties of the dot product, which we spoke about in another video, expanding this, so you get A dotted with B minus K multiplied by the dot product of B and B must equal 0. So that's just sort of expanding that B in. Okay, and then just rearranging for K. If we rearrange for K, subtract the dot product of A and B from both sides, and then divide by negative the dot product between B and B. And so you get K equals this just by sort of using properties of the dot product. Okay, and then we can say, therefore, that U, remember, U is equal to KB, and K is equal to this sort of coefficient here. vector A dotted with vector B divided by B, B dotted with B multiplied by vector B. So that's how we got to this conclusion. So this vector U is equal to this. This is how we work it out. Now there's just a bunch of alternate forms we need to know. So let's look. This first alternate form just says the following. You take the same A dotted with B, all right, divided by the magnitude of B squared. Well, just by comparing these, B dotted with B must be equal to the magnitude of B squared. And that should make sense by the definition of the dot product. If you've got the dot product between two vectors that are pointing in the same direction, the cosine of the angle between them is 1. Or should I say the angle between them is 0 and cosine of 0 is 1. So you'd get, in this case, it'd be B dotted with B equals the magnitude of B multiplied by the magnitude of B multiplied by 1. So it'd just be the magnitude of B squared multiplied by B. Okay, and then these are just, again, further rearrangements. If we sort of separate things a little bit, we could rewrite this in this form. Yeah, hopefully you can see that just by sort of breaking up the denominator. Yep, that hopefully checks out. And the important reason we did this is because the vector B divided by its magnitude is just a unit vector in the B direction. So A dotted with the unit vector in the B direction. Okay, B divided by B is again, B divided by the magnitude of B rather is just, it's just a unit vector in the B direction. Okay, so if we think about it like this whole thing, all of these things are what are called the vector resolute, but this little part here is what's called the scalar resolute, okay? Because this tells us the signed length of the vector. So it tells us whether it can be positive or negative, and it tells us how much we're scaling up the vector in the direction of B. So you've just got, yeah, this part here, this little first part here is what's called the scalar resolute, because that's going to tell you by how much you're scaling up that U vector, right? That U vector. How much do we scale it up in the direction of B? Okay, we can, and then it can also be negative, right? So it's the signed length. Okay, so that's a pretty challenging idea, I think, but hopefully that made some sense. Again, if you found this video at all useful, please give us a thumbs up or consider subscribing. We're over 100 subscribers now, so isn't that exciting? Yeah, and we'll keep this going. Let me know if you've got any questions, and I'll talk to you soon.